Good morning. Today in this section we will see the derivation of Maxwell's equation, which is very important. As far as Maxwell's equations are concerned, Maxwell has contributed a lot towards the study of electromagnetic waves. So his equations are very important in the study of M wave. So these are the four important equations of Maxwell. Del D equals rho, where rho is the volume charge density and D is your electric flux density. Then del B equal to 0, where B is a magnetic flux density, and del cross E is equal to minus dou B by dou T, where E is a electric field intensity, and del cross H is equal to J plus dou D by dou T, where H is a magnetic field intensity, J is the current density, and this term dou D by dou T is a displacement current density. Okay. Now we have to see the proof of this Maxwell's equation. We will start with Gauss law. So we know according to Gauss law, epsilon 0 integral E dot dA equal to the volume integral rho dV. Okay. So I am taking epsilon 0 inside, so I can write epsilon 0 dA is equal to volume integral rho dV. And we know what is d? D is equal to epsilon A, which is equal to epsilon 0 epsilon r into A. If the medium is air, then epsilon r is equal to 1. So finally I can write d is equal to epsilon 0 A. So instead of this epsilon 0, I have substitute area integral of d dot dA equal to volume integral rho dV. Okay. Now listen, here you can see a circle across an integral sign. That means that this is a closed surface. Okay, this is the standard notation of the integral across a closed surface. But even if you are simply putting it integral, then it's okay. But try to, if possible, try to draw this circle if the surface is a closed surface. Okay. Now coming to divergence theorem, we know the integral area integral of A dot dA equal to the volume integral of del A dB, where A is any vector. Now in our equation 1, B, electric flux density, is a vector. So I am going to rewrite the divergence theorem for D. So I can write area integral of D dot dA equal to volume integral of del D dV. Now I can equate equation 3 and equation 1. There you can see the left hand side is equal. So obviously the right hand side will also be equal. So I can write the volume integral of del dV is equal to the volume integral of rho dV. Okay, so both are volume integral. So finally I can conclude that del dot D is equal to rho. That's our first equation, Maxwell's first equation. Okay. Now next, Gauss law in magnetism states that the total magnetic flux in a closed surface is equal to 0. And this is how we mathematically represent it. That is, closed surface integral B dot dA is equal to 0, where dA is a magnetic flux density. Okay. Now using the divergence theorem, the surface integral can be replaced by volume integral, right? Because here you can see what is divergence theorem. Surface integral of A dA is equal to volume integral of del A dV, where A is any vector. So in this derivation, B is the vector. So instead of surface integral B dA, I can write what? Volume integral of del B dV, which is equal to 0. This is the divergence theorem. Okay. So making use of this divergence theorem, instead of area integral, I have substituted the volume integral of del B dV, which is equal to 0. From that I can write what del B is equal to 0. So that is Maxwell's second equation. Next, as per Faraday's law of electromagnetic induction, we have studied E is equal to minus d phi by dt, where E is the EMF or otherwise known as potential. We also know the relation connecting potential and electric field intensity we studied earlier, that is E is equal to integral E dl. This is a relation connecting what? Potential and electric field intensity. Now, the total magnetic flux linked with the closed path, if you are having a closed path like this, and this closed path is marked as C, okay, and the total magnetic flux inside this medium, is given by phi is equal to area integral of B dot dA. Okay, area integral of B dot dA. Now what I am going to do in the next step is I am substituting 5 and 6 in 4. Okay, what I am going to do, 5 and 6 in 4. So what is 4? E is equal to minus d phi by dt. So instead of E I will substitute integral E dot dl, and instead of phi I will substitute area integral B dot dA. So finally the expression will look like this. Line integral E dot dl is equal to minus d by dt of area integral B dot dA. Simply I am substituting 5 and 6 in 4. So in the next step what I am going to do is I am taking d by dt inside the integral. So I can write integral E dl is equal to minus area integral dou B by dou t into dA. When this d by dt is taken inside the area integral, becomes the partial derivative dou by dou t of B of dA. Now using Stokes theorem, you can write the left hand side as of equation 7, this as what? The closed area integral del cross E dA. You have studied that the Stokes theorem is equal to the the line integral of any vector will be equal to the surface integral of curl of that vector. That is your what? Stokes theorem. That is, the line integral of any vector will be equal to the surface integral of curl of that vector. This is your Stokes theorem. So what I am going to do is I am replacing this with Stokes theorem. So I can write integral del cross E dA is equal to closed integral minus dou B dou t of dA. So both side has become area integral. So finally I can write del cross E is equal to minus dou B by dou t, which is our third equation. Now next we will start with Ampere's circuit law, which we already studied. Integral B dot dl is equal to mu 0 I. We also know B is equal to mu 0 H if the medium is air. So what I am going to do is I am substituting B here, that is mu 0 H dl is equal to mu 0 I, that is this part. Mu 0 H dot dl is equal to mu 0 I. We also know that I, current, is equal to the area integral of current density J, which we studied earlier. I is equal to area integral of J dA, where J is a current density. So I am substituting I in this equation. So finally I can write integral mu 0 h dot dl is equal to mu 0 into, instead of this I will substitute closed integral of J dA. Okay, so mu 0 and mu 0 get cancelled, and I can write integral h dl is equal to integral J dA. Again I am going to apply the Stokes theorem to the left hand side of the above equation. You know, according to Stokes theorem, the area integral will be equal to the surface integral of curl of that vector, this one. The the line integral will be equal to surface integral of curl of that vector. So instead of integral h dot dl, I will be writing area integral del cross h dl, and the right hand side will remain the same, that is equal to area integral J dA. Okay. Area integral J dA. So finally both sides are having area integral, so I can write del cross h is equal to J. Ampere's circuit law is true for steady state and wrong for time varying current. This was proved by Maxwell, and hence the above equation was slightly modified to del cross h is equal to J plus dou D by dou T. Okay, so actually del cross h is equal to J. This equation is valid for steady current. So what Maxwell did was, this del cross h is equal to J was not valid for a time varying current. So what he did is, he slightly modified the equation del cross h so that it suits for both the steady current and time varying current. So accordingly the modified equation is written here, del cross h is equal to J plus dou D by dou T, where dou D by dou T is equal to JD is a displacement current density. And that's all about the derivation of Maxwell's equation. It's very easy as well as important too. Please study, and thank you. Now here you can see different representation of integral. Lesson here, as I said earlier, if you are having an integral with a circle and an A sign, that means it is a surface integral of a closed surface. Instead of A you can write S also, meaning is the same. Both these points towards a surface integral of a closed surface. And if it is marked as L, then this is a the line integral of a closed surface, and this is a volume integral of a closed surface. Another representation is for surface integral. In some text you can see two integral signs, and for volume there will be three integral signs. So in different textbooks they are using different notation, that's why I mentioned it here. If you see any three integral, then that will be volume. If two integral, that will be surface, and if one integral, then that will be line. Okay.